Welcome to the practice lecture for your exam. Because this material involves several different types of problems and writing chemical equations, in short, we're in chemistry land. I have started doing for this material an extra day or an extra lecture on just more examples. So let's go ahead and get started. The first few are you're going to be writing some chemical equations. We're going to recognize types of chemical reactions, and so on. We're going to work on stoichiometry and solutions, all the things that we've studied in exam 3 in terms of writing equations, stoichiometry, limiting reactants, percentage yield, and so on. Okay, so the very first one, we are combining sodium hydroxide with sulfuric acid. I encourage you to give this a try, stop the video, and then come back. So this is an acid and a base double replacement reaction. So I'm going to go ahead and write the equation. So double replacement, double date, switch dates. Hydrogens go with the OHs to produce waters. Since I have two hydrogens here, I know I'm going to end up with needing two OHs, and that will come into the, so I'll always produce water, and then the other combination is the salt. So indeed, sodium has a +1, sulfate has a -2, so that is why I needed two sodiums anyway. So I have a balanced chemical reaction, do a little racing here, so that I can write the info given in the problem under the species. So 0.75 molar sodium hydroxide, and the question is, how many milliliters? 275 milliliters of 0.5 molar sulfuric acid. This looks very familiar. I think we did this problem at the end of lecture 16, or one very similar to it. Okay. Well, we have our balanced chemical equation. If you're not in moles, get there. So the species or the substance that I can get into moles is this here, and then I will do my mole to mole step to answer this question for the sodium hydroxide. So when I have a molarity, rewrite it, trying to get to moles, so I'm leaving that as is. The volume needs to be converted to liters, 0.275 liters. So 0.5 times 0.275, 1.375, or 0.1375 moles. I will worry about significant figures at the end. So 1.375 moles, moving to the question, times 2/1. And the number of moles of sodium hydroxide I need is 0.275 moles. And I'm asked about volume, so when I take this molarity and rewrite it, and I'm going to do that up top here, I'm going to flip it over because I want the liter part on top and the moles on the bottom. And then when I multiply by the moles I just got, I will end up with liters, and then I can switch to milliliters, which is what the problem asked. Okay. And I get 366.7 milliliters. As my answer for number 1. All right. Going to scroll down to number 2. And give myself some room. Oops. All right. Again, give it a try. Turn off the video, give it a try, and then come back. I'm going to go ahead and start. So PB with a +2, that's what that Roman numeral is telling me, nitrate. So I need 2 of those -1 nitrates. How many grams are needed to fully react with, probably should put the word with in there, I'll do that in a minute, sodium chloride in the precipitation of lead 2 chloride, so they're telling you one of the products here, +2, chlorine's -1, so I need 2 of those. My other product is the sodium with the nitrate. Back to charges, +1, -1. Okay, I will balance, put a 2 here and a 2 here, and that should take care of the balancing. And then let me put some information, some additional information in from the problem. 23.5 milliliters, 0.55 molar. All right, so this is stoichiometry. If you're not in moles, get there. We're going to do that first here. Let me get a little shorter arrow so I have room to write my moles. So we're going to convert to moles using our molarity. 0.55 moles times, per liter, sorry, times 0.0235 liters, switching those milliliters to liters. So I get 1.29 times 10 to the minus 2 moles. And that goes right here. Then you're going to move what is your mole ratio, what you're moving to, over what you're coming from. And the number of moles of the lead nitrate that are needed is 6.46 times 10 to the minus 3. And they want grams this time, so get your periodic tables out. Okay, 207.2, I'm going to do that up here. So 207.2 for the lead, 28 for the 2 nitrogens, 96 for the 6 oxygens. And I end up with 331.2 as my molar mass. Grams per mole. And I will take those grams per mole, I will take those moles, so 6.46 times 10 to the minus 3 moles times the 331.2 grams per mole, and that will give me my grams. And I get 2.14 grams as an answer to number 2. 2.14 grams of lead nitrate. All right, moving on to number 3. And we put that, we're needed to react, to fully react, put that in there, with. Okay. Okay, whatever. Some more room here. Do a little scrolling. All right. New problem. We've got barium chloride, barium +2, chlorine -1, so there's my formula. Ammonium phosphate, 2 of your polyatomic ions. Ammonium, I've written the formula, now focus on the charge. Phosphate, I've written the formula, now focus on the charge. I've got a -3 on this side, +1 on the left. I need 3 of those +1s to cancel out that -3. All right, double replacement again. Barium phosphate is one of the possibilities, and it is our precipitate according to the solubility rules. So barium +2, phosphate. Focus on the charges. I got a +2, -3, so I need to knit 3 of the bariums and 2 of the phosphates. And then my other combination is ammonium chloride, NH4 with a +1, chlorine with a -1. Okay, this is my solid, those are our correct formulas. Now I will balance. I've got 3 bariums and 2 phosphates, so I'm going to have to put a 2 here, and I'm going to put a 3 in front of the barium, so that gives me 6 chlorines. I have 6 ammonium ions, so that works out perfectly because chemistry is cool like that. All right, now putting in the information, how many milliliters? 0.4 molar, 175 milliliters, 1.50 molar. All right. This is our third one in a row, same type. Get into moles. You're not moles, get there. 1.50 moles per liter, rewriting the big M, times the liters, dividing by 1,000. And that's going to give me my moles of the ammonium phosphate. And I get 0.263 moles. Okay, so that goes here. All right, mole ratio. What I'm moving to has a 3 in front of it. What I'm coming from has a 2 in front of it. And I end up with 0.394 moles. Okay, so now you need to take these two pieces of information and get milliliters out of it. So rewrite the big M, but since I want volume, I'm going to flip it over. 1 liter has 0.4 moles. I just got the number of moles, so 0.394, and then switch it into milliliters. Everything cancels. Okay. And I end up with 984 milliliters. I'm going to check that one more time. It looks about right given the big difference in the molarities, 1.5 versus 0.4, but I just want to double check it because it just does seem a little large. Okay. Okay, so far so good. I got the same answer. Okay, we're done. 984 milliliters of the barium chloride. Okay. Alrighty, looks very similar, except we're going for grams this time. Alrighty, so cobalt 3 nitrate, cobalt with a +3, that's what this Roman numeral means. Nitrate, NO3, focus on the charge. I need 3 of those negative ones to cancel out the +3. Plus sodium sulfate, Na +1, sulfate -2, so I need 2 of those. Double replacement, cobalt goes with the sulfate. Charges don't change in double replacement. Focus on the charges. I need 2 of the cobalts, and then I'll need 3 of the sulfates to make that formula work. Sodium nitrate is my other product. Sodium with a +1, nitrate with a -1. So this is One of the reasons why I make you memorize some of those polyatomic ions is because it's just part of the language, and it just wastes so much time when you have to look these up and so on, when you could be spending more time thinking about how to work the problem. All right, we've got 3 nitrates, 2 sodiums, we got 3 sulfates over here, so let's start with that. 3 here gives me 6 sodiums, so I'm going to put a 6 there. I've got 2 cobalts, so I'm going to have to put a 2 here, which gives me the 6 nitrates. If you have the correct formulas, it'll balance out so easily. All right, so we've got 53 milliliters of the cobalt nitrate, 0.75 molar. And our question is, how many grams of this solid will we precipitate? All right, switch this into moles. 0.75 moles per liter times 0.053 liters. And I end up with 3.98 times 10 to the minus 2 moles. And now I can move to my question, which is over here, times, there's a 1 in front of this, 1 over 2. And I end up with 1.99 times 10 to the minus 2 moles. And then I have to convert that to grams. So we have our box stoichiometry problem. So I'm going to add up the molar mass over here. Okay, cobalt is 58.93 times 2. And I went ahead and carried it out a couple more decimal places. So 117.87 for the cobalts. Okay, plus 3 sulfurs. Sulfur is 32.06. 96.18. One of the reasons that I'm being a little more, that I'm carrying my molar masses out a little bit more, is how large the molar mass of this is going to be. So, you know, it would introduce a lot of error if I did if I rounded more. All right, 12 oxygens times 16 is 192. All right, so adding all that up, and I end up with 406.1 grams per mole for the cobalt sulfate. So times 406.1 grams per mole. And I end up with 8.08 grams as my answer. Okay, number 4. Alrighty, moving on to number 5. Give myself some more room here. Okay, another double replacement. Aluminum hydroxide, aluminum plus 3, hydroxide minus 1. I need 3 of those negative 1s. HCl. Okay, hydrogen goes with the OH. I see I have 3 OHs here, so I know I'm going to make at least 3 waters. And the other product is aluminum chloride. Aluminum plus 3, chlorine minus 1. I need 3 of those. So 3 chlorines. So if I put a 3 here, 3 hydrogens plus 3 hydrogens is 6. And then there's the 3 oxygens. So we're all balanced. So how many grams of this? And then 45.3 milliliters, 0.55 molar. All right. Getting into moles by rewriting the big M, converting my volume to liters. .49 times 10 to the minus 2 moles. So 2.49 times 10 to the minus 2 moles. Okay, using our mole ratio times, there's a 1 here and a 3 here, so dividing by 3. And I end up with 8.31 times 10 to the minus 3 moles of the aluminum hydroxide. And then I will convert to grams. So we have our box using the molar mass of aluminum hydroxide. So aluminum is 26.98 plus the 3 oxygens is 48 plus 3 hydrogens. So we have 78.01 is my molar mass. So times 78.01, and that will be my answer. Okay, 78 grams per mole times the 8.31 times 10 to the minus 3 moles. The moles cancel, and my answer is 6.48, 0.648 grams. That's a very small number of moles. Okay, so 0.648 was our final answer. All right, number 6, moving out of pretty repetitive set of stoichiometry problems. All right, so we're going to write balanced equations and net ionic equations for each of the following solution mixtures. If no precipitate forms, write no reaction. Let me remind you that if no precipitate forms, then you have the same 4 ions floating around in the solution that you had before, because all of these reactants are soluble. Okay, so the first thing we want to do is look to see, is ammonium nitrate soluble? Yes, it is, but barium sulfate, if you check your solubility rules, is not. So a reaction happens in A. Okay, if you're still having a little bit of trouble changing these, doing these double replacement switch ups, sometimes going back to doing the words helps a lot, because you're not distracted by the formula. So ammonium goes with nitrate and barium goes with sulfate. Barium sulfate is a exception for sulfate solubility. Most sulfates are, but barium is an exception. All right, so we're going to need more room if we're going to do a complete ionic and a net ionic. Oops. All right, so I'm going to go ahead and do the regular, lost my words, oh well. NH4 with a +1, sulfate with a -2, so I need 2 of those ammoniums, plus barium nitrate, barium +2, nitrate -1, 2 of those. Okay, ammonium nitrate, the soluble product, +1 -1, so this is aqueous. And then barium and sulfate, barium is +2, sulfate is -2, so one of each is good, and that's my solid. These over here are aqueous, so we're going to now split things up. I'll get it back, don't worry. Okay, so complete ionic equation. Oops. 2, that 2 comes in front of the polyatomic ion. 2 ammoniums plus a sulfate plus a barium ion plus 2 nitrates. Oh, we didn't balance. Need a 2 here. And we're good. Okay, so then distribute that 2 ammoniums plus 2 nitrates plus leave the solid alone. Okay. Spectator ions are the ammonium and the nitrates, and then we're left with our net ionic equation, which are the ions that formed the precipitate. All right, so this is what we're going to do for each one of these. Okay. All right. Lead 2 nitrate and sodium chloride, lead chloride and sodium nitrate. Sodium nitrate is soluble, but lead is an exception for the chlorides, and that is my precipitate. And it's still lead 2 because charges don't change in double replacement. All right, so translating, Pb with a plus 2, that's what the Roman numeral means, nitrate minus 1, need 2 of those nitrates, plus sodium chloride, plus 1 minus 1, sodium nitrate, plus 1 minus 1 again, and then lead 2 chloride, Pb with a plus 2, chlorine with a minus 1, so I need 2 of those. All right, balancing, 2 here and a 2 here, and that should do it. All right, breaking up into ions, Pb with a plus 2, bring the subscript for the polyatomic ion in front, distribute the 2 sodium ions, 2 chlorine ions, distribute the 2 here, 2 sodiums plus 2 nitrates, and then you get to leave the solid alone. All right, so my spectators are sodium and nitrate, and then I end up with lead plus the chlorines to give me the solid. All right, looking at C, I'm not going to scroll just yet. I think I've got enough room here. In fact, I don't need much room at all because sodium nitrate is soluble. That's one possible combination. And potassium, both sodium and potassium are from group 1. There is no reaction here because I did not get a precipitate. So I don't need all that space. All right, so let me get rid of some of that space. And a little bit more here. Are we going to need the space for D? I see sodium and rubidium. Rubidium is from group 1 as well. So sodium chloride and rubidium bromide are both soluble. So we still have the same 4 ions floating around in solution. So no reaction on C, no reaction on D. Okay, E does have a reaction. So let me get rid of a little space here, get some more under E. Oops. And do a little scrolling. Okay. All right, so we do have a precipitate in E. Copper 2 hydroxide is our precipitate. If you look on your solubilities, most hydroxides are not soluble. So this is our solid. Oops. Plus sodium chloride, which of course is soluble. All right, translating into formulas. Cu with a plus 2. Chlorine with a minus 1, so I need 2 of those chlorines, plus sodium hydroxide, copper 2 plus 2 hydroxide. OH has a minus 1 charge, So I need 2 of those -1s, and that's my solid, plus Na with a plus, chlorine with a minus, and this is aqueous. Of course, our reactants are aqueous as well. Okay, balancing. I need a 2 here for the hydroxide, and a 2 here for the chlorines, and that should do it. All right, complete ionic equation, Cu plus 2, plus this 2 comes in front of the chlorine, so plus 2 chlorine. Distribute this 2 to both ions in this formula, the sodium ion and the hydroxide. I cannot emphasize enough how important it is to be putting the charges in now. It will make the next material we do so much easier for you. Distribute this 2 to both those ions. All right, your spectators are the sodium and the chlorines, and then we end up with copper and some hydroxide. It makes the solid. Okay. Scrolling. All right, in number 7, we are writing a balanced chemical equation for each of the following and determine the type of reaction. Okay, so we are going to finish it up and talk about the type. Some of them we're just writing equations, some of them we have to come up with the products. And I will remind you of the types. Basically, you need to be able to do double replacements, and you need to be able to finish combustion reactions. So the only types that I'm asked you to finish is this. A is a double replacement. B is a combustion. So you need to be able to do both those types for your exam. All right, double replacement here. Aluminum goes with sulfate. So aluminum is a +3. Sulfate is a -2. So I need 2 of those +3s and 3 of those sulfates. And my other product is water. This is an acid base. So H2O. 3 sulfates. If I put a 3 here, I got to put a 2 here for the aluminum, put a 3 here for the sulfate. That gives me a total of 6 OHs, and I've got a total of 6 Hs, so I make 6 waters. Now, it does not ask to do net ionic or anything. This is a double replacement. So we're just writing the balanced chemical equations and determining the type of reaction. B, combustion of a hydrocarbon always produces CO2 and water. Balance carbons first. Balance hydrogens next. So I have 4 plus 2 is 6 oxygens. And that will balance, and this is combustion. Okay. Mercury 2 oxide, Hg with a +2, oxygen with a -2, so that's our formula. Goes to mercury, that's just an element that comes as atoms, and don't forget that this is one of our diatomics. Balancing. And what type of reaction is this? I see one thing becoming 2. This is decomposition. All right, I see 2 compounds here, and you're expected to be able to finish it, so that tells me double replacement. Potassium nitrate is one of my products. The other product is silver chloride, which would be the precipitate. All right, so writing our equation, silver +1, nitrate -1. In fact, everything in this reaction is +1 -1, so that makes it nice and easy for balancing. Basically, we're done. And this is a double replacement. All right, what type of reaction do we have in E? I see element, compound, new element, different compound. So that tells me single replacement. Somebody went alone to the dance and took hydrogen's date, and then hydrogen went home alone as the element, as the new element. So calcium plus HCl to make H2, hydrogen the element comes two at a time. Calcium chloride charges. And now to balance. And that does it for me. So number E is single replacement. I'm going to scroll. All right, F, see another combustion reaction. It can contain, this compound here can contain oxygen, so always CO2 and water. Balance your carbons first. I have a total of 6 hydrogens, so I'm going to put a 3 here. Now this brings up the trick for balancing oxygens when you end up with an odd number. 4 plus 3 is 7. So what I'm going to do is I'm going to put that odd number in front of O2 and then multiply all of the other coefficients by 2. Okay, so this becomes 4, and that was 3, so now it's a 6. And if I check 4 carbons, 4 carbons, 6 times 2 is 12, 6 times 2 is 12 for the hydrogen, and 8 and 6 is 14. And this is combustion. We know it's combustion because we have oxygen as a reactant, producing CO2 and water. All right, moving on. Okay. What type of reaction do we have in G? I see element, compound, new element, different compound, so this tells me single replacement. Hydrogen, H2, and I don't know why I gave you the formula for iron 3 oxide, I'm slipping. Iron is my new element, and hydrogen and oxygen come together to form water. Steam is just water as a gas. All right, balancing. I have 2 irons over there, 3 oxygens, so that gives me a total of 6. So I'm going to put a 3 here. All right, so this is just a little language practice, types of reactions, and balancing. All right, I see 2 things becoming 1 here. This tells me it is synthesis. Carbon plus oxygen, the element, is O2 to produce carbon monoxide. So I'm going to put a 2 here for the oxygen and then a 2 here for the carbon. One more, looks like our familiar double replacement. Aluminum goes with hydroxide, plus 3 for aluminum, negative 1 for hydroxide, times 3, plus calcium sulfate. I need to switch that to a lower case, a subscript. Calcium has a plus 2, sulfate has a minus 2, so that's good. Calcium sulfate is, I think we're actually producing 2 solids here, but we're gonna, that's not important. All we're doing is writing equations and balancing. This is definitely double replacement. Balancing, I have 2 aluminums on this side, so I'll start there. I have 3 sulfates, so I'll put a 3 here. All right, so I need a 3 for the calcium, and that gives me 6 oxygens and hydrogens, and I've got that here with 2 in front and then this 3. So we are good with the balancing. Let me do a little fixing here. So you're going to lose what I've written. So go ahead and pause if you need to and write down what you've missed. All right, it's just bothering me. Alrighty, let's move on to number 8. Now, of course, this is a lot at one time. If you want to, you always have the option of stopping the video and coming back to this later. All right. So here's our balance. You're given a balanced chemical equation here. I'm going to write the info in the problem where it needs to go. 9 grams of aluminum, 30 grams of aluminum phosphate are produced. So you are given an amount of a product. This 30 grams is, and then they ask you what is the percentage yield. So this is the actual. You either have to be given a percentage or the actual. You are never given the theoretical. We're about to do that. So 9 grams, get it into moles. Aluminum weighs 26.98. So 9 divided by 26.98. And I've got 0.334 moles. Okay. I need the theoretical yield of the aluminum phosphate, so my mole ratio is times 2/2. So same number of moles. Okay. I need the molar mass of the aluminum phosphate rather. Aluminum, don't use the coefficients here. I just used them the only time they need to be used. Plus phosphorus, 30.97, and then 4 oxygens. And I get 121.95 as the molar mass, grams per mole, times 121.95 grams per mole. Moles cancel. And I end up with 40.73 as my theoretical yield. So every time you do, grams, a stoichiometry problem, I don't know why it's just like slowing down. It's weird. That's weird. Okay. Percentage yield is actual over theoretical, so 30 over the 40.73 times 100. And I end up with 73.66%. Oops, 73.66. Or 0.7%. All right, never given the theoretical yield. If you're given the amount of a product produced, put it off to the side, that is your actual yield, and then you will be finding out how many grams of that same product you make, which is your theoretical yield. Okay. So same equation looks like for number 9. So what I'd like to do is erase what I've done here for number 8, since I'm using the same equation. So pause if you need to at this point. I'm going to use the big eraser. Now I'm going to leave this molar mass up here because I might need that again. So I'm going to use the big eraser, erase all the stuff. All right. So this time, oops, the number subscript need to change. 100 grams of the phosphoric acid, 25 grams of aluminum. So they want to know what is the limiting reactant, and then your favorite question, how much of the excess reactant is left over. Switching both to moles. Okay, already got the aluminum molar mass. My phosphoric acid molar mass will be 3.03 plus 30.97 for the phosphorus plus 64 for the oxygens. And I end up with 98.01. So I will take 25 grams divided by the molar mass, I'm just showing you with this one that we need to divide using the units. And I end up with 0.927 moles of the aluminum. And for the phosphoric acid, I end up with 1.02 moles. Now, what we do at this point is we divide by the coefficients. We have the same coefficient here, 2 and a 2. So that automatically makes the aluminum the limiting reactant. Okay? To determine the amount of the excess left over, I am going to move from the limiting to the excess. So it would be times 1 over 1. Okay? So I'd go times 1 over 1, which is how much I use. So I will be subtracting that from my original amount. Okay? So 1.02 minus the 0.927, and I have 9.3 times 10 to the minus 2 moles left over. So let me reiterate again what we've done. When you have to determine how much of the excess is left over, go to the limiting reactant. You have to figure everything in the problem out from the limiting reactant. Move using the mole ratio to the excess. That amount you get is the amount you use. Subtract it from the original, and now I'm going to switch it back to grams. Because usually when they ask how much, it means grams. Okay? So that's why it's nice having those molar masses written at the top. And that is 9.11 grams left over. Okay? All right, that's number 9. Moving on to number 10, scrolling. Oh. Okay. The one thing I want to fix from the previous, here we go. Make that into a sub. Okay. All right, let me get myself some room here. When octane is burned in oxygen, carbon dioxide and water are produced. If 320 grams of octane is burned and 392 grams of water is recovered, what is the percentage yield? All right, so let's put this information in. So we have 320 grams of the octane, and they're giving us an amount of a product. So again, this is the actual. My job is to get the theoretical for the same product and then get the percentage at the end. Okay, so we know it'll be 392 grams on top. We've got to get the theoretical. You know, and moles get there. Okay. And I get a molar mass of 114.27 for the octane. So 320 divided by that to get moles. 2.8 moles. Okay. Moving to my question, times, big coefficients here, 18 over 2, so that's like multiplying times 9. And I get 25.2 moles. And of course, we know that water weighs 18, actually 18.02. And so we'll multiply times that molar mass. All right. And I end up with 454.2 or just we'll leave it as 454 grams is my theoretical. So that will go here, times 100. So I end up with 86.3% for my percentage yield. All right, so we did a box with our stoichiometry problem there. All right, scrolling. All right, number 11. Almost done, 2 more. So we're doing aluminum nitrate with sodium hydroxide. All right, so a precipitation reaction essentially. So aluminum, well, it's actually an acid base, but we won't talk about that at this point. Just a different kind. So aluminum goes with double replacement. Aluminum goes with hydroxide. Aluminum's +3, hydroxide's -1, so I need 3 of those. Of course, you've got that right there. And then my other product is sodium nitrate. Sodium's +1, nitrate is -1. Balancing, I need 3 of those nitrates. Got 3 hydroxides there, but I needed the 3 sodium, so that looks good. Okay. Determine the percentage yield if 2.8 grams of this, and again we are given the amount of, that looks terrible, of a product, which of course is your actual yield. So 0.996 grams is your actual. We have to get a theoretical, so get this into moles. All right, so molar masses, 26.98 for the aluminum, 3 nitrogens is 42, and 9 oxygens is 144. And I end up with 212.98 as my molar mass. Grams per mole. So I'll take my 2.8 grams and divide by that, so very small amount, 1.31 times 10 to the minus 2 moles. All right, and then I'll move to my question, times 1 over 1. So 1.31 times 10 to the minus 2 moles of aluminum hydroxide, molar mass, 26.98 aluminum, 48 for the oxygens, 3.03 for the hydrogens. And that is 78.01 for a molar mass. So times 78.01 grams per mole. Moles cancel, and this will be my theoretical yield. And I end up with, looks like 1.02 grams. Okay, so percentage yield equals actual over theoretical. Of course, the grams cancel, times 100. And I end up with 97.6 as my, actually it's 97.65, so I guess we could say 97, I'm sorry, 97.7. 97.7%. All right, never given the theoretical, you must obtain that yourself. All right, one more, and we have finished practicing for exam 3. You will, of course, have your review, but Students' first exposure to chemistry land can be pretty, it's a lot to take in. So a little extra practice never hurts. Okay, so let's scroll and do our last problem. Okay, so it asks, what is the expected yield? What is the percentage yield? All right, is the question. So a student places an iron nail, 2.32 grams, into a flask of copper sulfate. The nail reacts completely. The student finds the mass of the recovered copper to be 2.51 grams. So again, this is your actual. We need to find our theoretical by converting this amount that we were given into moles first. Of course, iron is 55.85 is the molar mass. So 2.32 divided by 55.85, and I get 4.15 times 10 to the minus 2 moles. All right, so 4.15 times 10 to the minus 2 moles of the iron. Moving over to the copper times 1 over 1. So 4.15 times 10 to the minus 2 moles of the copper. Copper's molar mass is 63.55 grams per mole. So multiplying, our moles cancel. So I end up with 2.64 grams of copper, which is my theoretical. So to get my percentage, so that's my expected yield. My percentage yield is the actual over the theoretical times 100. And I end up with 95.1%. And that concludes our exam 3 practice.